In the previous lessons, we introduced the concept of the mole and saw how we can use the mole concept with a balanced equation. Using the coefficients from a balanced equation, we can relate the amount in moles of one substance in a balanced equation to the amounts of all other materials consumed or produced in the reaction. In this lesson, we're going to expand on this idea. We're going to look at one very common type of problem and explore strategies for simplifying this type of calculation. One important type of stoichiometry calculation is the gram-to-gram problem. In this type of problem, we are given the mass of one reagent or product in grams and asked to find the mass of another reagent or product, also in grams. To solve this problem, we must first convert the grams of substance A into moles of A. We then relate the moles of substance A to the moles of substance B, using the mole ratio from the balanced equation. Finally, we can convert from moles of B to grams of B using the molar mass. Let's look at an example of this type of problem. When heated with a Bunsen burner, magnesium carbonate decomposes to magnesium oxide and carbon dioxide, as shown in this equation. If 5.24 grams of magnesium carbonate are heated in this manner, how many grams of magnesium oxide can be produced? This question gives us the grams of magnesium carbonate and asks us for the grams of magnesium oxide. To calculate the grams of magnesium oxide, we must first convert the grams of MgCO3 to moles of MgCO3. We can then relate this to moles of MgO and then convert to grams of MgO. We begin with 5.24 grams of MgCO3. To convert to moles of MgCO3, we multiply by 1 mole of MgCO3 over 84.32 grams of MgCO3. The grams of MgCO3 cancel. We then convert to moles of MgO using the ratio in the balanced equation. 1 mole of MgO per 1 mole of MgCO3. The moles of MgCO3 cancel. Finally, we convert to grams of MgO using the molar mass. 40.31 grams of MgO per 1 mole of MgO. The moles of MgO cancel. This gives us a final answer of 2.51 grams of magnesium oxide. For many people, stoichiometry problems can seem overwhelming. Don't worry, you can do this. The key to solving these problems is to recognize the simple patterns, then follow the patterns every time. All of the stoichiometry problems that we've done so far rely on just 3 types of conversions, each with its own conversion factor. If we need to convert between grams and moles of one substance, we use the molar mass. If we need to convert between moles and particles of one substance, we use Avogadro's number. And if we need to convert between 2 different substances, we use the mole ratio from the balanced equation. Stoichiometry problems provide the amount of one compound, A, and ask us to relate this to the amount of another compound, B. These problems can be solved by using the mole map shown here. Like any map, this guide helps us locate where we are going, and how to get there. For example, how do we get from grams of compound A to particles of compound B? Looking at the mole map, we can see this requires 3 steps. Beginning with grams of A, we must convert to moles of A, then to moles of B, and finally to particles of B. Let's look at one more example. Zinc metal reacts with aqueous copper 2 chloride, as shown in this equation. If 3.03 times 10 to the 21st atoms of zinc react, how many grams of zinc chloride will form? Show the sequence of conversions necessary, then calculate the numerical answer. This question gives us the number of atoms of zinc. It asks us how many grams of zinc chloride will form. From the mole map, we can see that we are given particles of one species. Let's call it particles of A. We're asked for the grams of another species, that is, grams of B. From the mole map, we see that we must go from particles of A to moles of A, to moles of B, to grams of B. For our problem, this means that we must go from atoms of zinc to moles of zinc to moles of zinc chloride, and then to grams of zinc chloride. Now that we have our strategy in place, let's solve this problem. We begin with 3.03 times 10 to the 21st atoms of zinc. To convert to moles of zinc, we must use Avogadro's number. We multiply by 1 mole of zinc over 6.02 times 10 to the 23rd atoms of zinc. The atoms of zinc cancel. Next, we must convert to moles of zinc chloride. From the balanced equation, we see that we form 1 mole of zinc chloride for every 1 mole of zinc. The moles of zinc cancel. Finally, we convert to grams of zinc chloride. To do this, we multiply by the formula mass of zinc chloride. 136.28 grams of zinc chloride over 1 mole of zinc chloride. The moles of zinc chloride cancel. This gives us a final answer of 0.68 grams of zinc chloride. To summarize, we can use the mole map like the one here to solve any stoichiometry problem that relates grams, moles, and particles. Notice that we only have 3 types of conversion factors for these problems: the molar mass, Avogadro's number, and the mole ratio, that is, the coefficients from the balanced equation.